Hello class, my name is Amir Zareh, and I will be talking to you about the proper dilution and neutralization of hazardous solutions. To fully acquaint ourselves with this subject, we must first understand what acids and bases are. An acid is a substance that forms hydrogen ions when dissolved in water in a process called ionization. They react with bases to form salt and H2O, conduct electrical currents, are sour in taste, and have a pH under 7. Examples of acids include sulfuric acid, which is found in car batteries, hydrochloric acid, which is in stomach acid, and carbonic acid, which is found in carbonate water. A base, on the other hand, is a substance that forms hydroxide ions when dissolved in water in a process called dissociation. Bases react with acids to form salt and H2O, conduct electrical currents, are bitter in taste, and have a slippery texture. Bases also have a pH over 7. Examples of bases include drain cleaner, which is sodium hydroxide, and baking soda, which is sodium bicarbonate. Acids and bases are divided up into two categories. There are weak acids and bases, and there are strong acids and bases. A strong acid or base is an acid or base that completely dissociates into ions in water. Examples of this are hydrochloric acid and sodium hydroxide. A weak acid or base is an acid or base that slightly dissociates into ions in water. Examples of this is acetic acid and ammonia. Hydrogen ions that dissociate from acids bond with surrounding water molecules to form hydronium. So the concentration of hydronium in a strong acid solution is equal to the concentration of the acid, and the concentration of hydronium in a weak acid solution is less than the concentration of the acid. Similarly, the concentration of hydroxide ions in a strong base solution is equal to the concentration of the base. The concentration of the hydroxide ions in a weak base solution is less than the concentration of the base. To measure the strength of an acid or base, a pH scale is often used. A pH scale is a scale ranging from 0 to 14, used to measure the strength of an acid or base. The lower the value, the more hydrogen ions are present in the substance. Substances with a pH less than 7 are acidic and become more acidic as the value decreases. Substances with a pH higher than 7 are basic and become more basic as their value increases. Substances with a pH of 7 are referred to as neutral. To measure the pH of a substance, pH indicators are often used. One example of a pH indicator is litmus paper. Litmus paper is a water-soluble mixture of lichen dyes absorbed onto filter paper used to test substances for acidity. Blue litmus paper turns red in an acid with a pH less than 4.5. Red litmus paper turns blue in a base with a pH of more than 8.3. Another more useful pH indicator is a universal indicator. A universal indicator is a filter paper that is absorbed with several compounds that exhibit smooth color changes. They cover a value range from 1 to 14 to indicate the acidity or basicness of a substance. So if a universal indicator was to be placed in a pH range of 0 to 3, it would turn red. In 3 to 6, it would turn orange-yellow. In 7, it would turn green. In a pH of 8 to 11, it would turn blue. And in a pH of 11 to 14, it would turn purple. Other popular indicators include phenolphthalein, which is a chemical compound which is colorless in substance with a pH less than 8.2, but become bright pink in a base with a pH of more than 10. Another popular pH indicator is bromothiamyl blue. Bromothiamyl blue is an indicator for weak acids and bases. It appears yellow in a solution with a pH less than 6 and becomes blue in a solution with a pH greater than 7.6. A pH indicator used to test acids is methyl orange. This appears red in a solution with a pH less than 3.1 and appears yellow in a solution with a pH greater than 4.4. pH indicators can also be found in nature. Many colored plants contain anthocyanin, which is a compound that turns red in acids and blue in bases. For instance, hydrangea plants indicate the pH of the soil they grow in. Red hydrangeas grow in acidic soil and blue hydrangeas grow in basic soil. Other plants and plant parts that are pH indicators are blueberries, red cabbage, rhubarb, roses, and poppies. Here is a video that will show the acids and base indicators. Here is a short video illustrating acids and bases in action.
This is acid-base indicators. We're going to look at methyl orange, methyl red, bromothiamyl blue, litmus, phenolphthalein, and indigo carmine. The pH range that we see here is the pH at which the changes actually occur. So if you're looking at something very acidic, you would be using methyl orange, and it works its way to litmus, which is pH 7. The change takes place at pH 7. Indigo carmine is a much higher pH, closer to an 11, 12, or 13 base. So hopefully our hydrochloric acid and sodium hydroxide are going to be able to indicate or show us at least some color changes, what to expect. If we start with methyl orange, we're going to see that in the acid, methyl orange turns a nice red, whereas in the sodium hydroxide, it is a yellow. At a little bit higher pH, but it'll still give us the indication, a methyl red will give us a red, and in the sodium hydroxide, we've got yellow. Our bromothiamyl blue, we'll do these here. Our bromothiamyl blue in an acid gives me a yellow color, and in a base, it stays a pretty blue. While we're on this tray, let's just check our litmus paper, just to make sure we've got our acid. Here's our acid, and here's our base. We'll compare them to our acid-base indicators, and we see that our sodium hydroxide is a very high base, at least an 11 or 12, anything above a 10 for sure. And our hydrochloric acid is about a 2. We've got 2 more indicators. We've got phenolphthalein to try, and I'll show you that. Our phenolphthalein, it doesn't do much. It goes white, if anything, or clear. It'll clear up here, whereas phenolphthalein in our sodium hydroxide turns a pretty red, pink, okay, fuchsia. Our indigo carmine, okay, our indigo carmine is going to turn, it's a blue solution, and it will stay blue. Here, I should show you more. It will stay blue in an acid solution, whereas a base, okay, we get a nice, it turns a...
Okay. When acids and bases react, a neutralization reaction occurs. A neutralization reaction is a double displacement reaction between an acid and a base to form water and an ionic compound. The ionic compound, or better referred to as a salt, is formed from the anion of the acid and the cation from the base. An example of this is when nitric acid reacts with sodium hydroxide to form sodium nitrate and H2O. If a strong base was to react with a strong acid in the mole ratio from a balanced chemical equation, a neutral aqueous solution of a salt is formed. Acid and bases of different strengths will not form a neutral solution. Some acids and bases are very corrosive and therefore are very hazardous substances and can often damage the environment or harm humans. When an acid or base spill occurs, a neutralization reaction can be used to diminish the hazard. Strong acids or bases should never be used to neutralize a chemical spill because they may create a hazardous spill of their own. Neutralization reactions involving strong acids and bases are also very exothermic, so therefore they form heated solutions and fumes, thus posing another hazard. Popular weak acids used to neutralize base spills include sodium hydrogen sulfate and citric acid. Popular weak bases used to neutralize acid spills are sodium bicarbonate and calcium carbonate. Acid-base indicators should be used to determine if an acid or base has been fully neutralized. Another method of preventing accidents and hazards is dilution. Dilution is the act of making a solution less concentrated by adding more solvent to it. Highly concentrated acids are usually diluted to reduce the hazard of substance so it could be worked with and disposed of safely. Two major precautions should be taken when diluting acids with water. First off, concentrated acids should be diluted under a fume hood to prevent the diluter from breathing in the fumes released. This is because acids can form in airways and lungs if inhaled. Secondly, acids should always be added to water and never the other way around. This is because acids reacting with water is a very exothermic reaction, and water is less dense than acid. Therefore, if water was added to acid, it would float on top, boil because of the heat, and splatter. When acid is added to water, it sinks into the solution, and heat generated is spread throughout the solution. An example of acid dilution is the dilution of muriatic acid, which is highly concentrated hydrochloric acid with a molarity of 12 moles per liter. Before commencing dilution, two major points should be taken. The number of moles of a solute does not change with the amount of solvent added, so therefore the amount of initial solute is equal to the amount of final solute. The second point is that to find the amount of solute, the formula of N equals concentration times volume must be used. So to say we wanted to find out how much hydrochloric acid should be used to create a 0.65 liter solution with a molarity of 3 moles per liter. To find the solution to this problem, we must use the formula concentration initial times volume initial equals concentration final times volume final. After using the formula and doing the calculations, we can see that 0.1625 liters of hydrochloric acid should be used. To find the amount of solvent that should be used, we must take this number and take it away from our total volume, which is 0.65 liters. After doing the calculations, we can see that 0.1625 liters of hydrochloric acid must be added to 0.4875 liters of water to create a solution with a molarity of 3 moles per liter. You have now been informed about the proper dilution and neutralization of acids and bases. Thank you for listening to this presentation.